Did you ever stop to think about what happens to cryogenic liquids during the loading, offloading, and storage process? Probably not. So much of the process is not visible and must be taken for granted. Most training programs teach the mechanics of equipment operation and the theory of fluid behavior with an emphasis on safe handling. But the opportunity to actually see what takes place on the inside has been missing. What you've been observing is the external world of cryogenics. Until today. Welcome to the inner world of cryogenics. This is a transparent working model of a cryogenic trailer and a typical storage tank. They were designed and built by Air Products to demonstrate the actual behavior of cryogenic liquids. What you are about to see has been done under controlled laboratory conditions, using appropriate engineering disciplines to design, construct, and test these units. Do not attempt to duplicate these demonstrations. The fluid we're using is not a cryogenic liquid, but it behaves in the same manner when subjected to changes in temperature, pressure, and containment. With the aid of these working models, we are going to demonstrate various thermodynamic processes such as condensation, vaporization, pump cavitation, subcooling, heat leak, liquid growth, product saturation, equilibrium, stratification, and even product flash loss. But before we begin, let's define some of the more important terms that we'll be using. Cryogenics, a branch of engineering that relates to the production and effects of very low temperatures, usually minus 238 degrees Fahrenheit and colder. Condensation, the conversion of vapors into liquid by cooling the vapors. Vaporization, the conversion of liquid into vapor by warming the liquid. Equilibrium, a state where the liquid and gas phases coexist at the same temperature and vapor pressure. Saturation, a state where the liquid and gas phases coexist in equilibrium. Vapor pressure, the pressure of a liquid in equilibrium with its own vapor. The vapor pressure is a function of temperature. Subcooling, raising gas space pressure above the normal vapor pressure of a saturated liquid, creating net positive suction head, NPSH. Cavitation, partial or full loss of pump prime due to insufficient subcooling or net positive suction head. Depressurization flash loss, vaporization caused by reducing the gas phase pressure to something less than the saturated vapor pressure of the liquid. Stratification, a vertical temperature gradient with colder product at the bottom and warmer product at the top. Liquid density, the weight per unit of volume, such as pounds per gallon. Entrainment, liquid droplets carried along with a flowing gas stream. Don't be alarmed if some of these terms seem too technical and confusing. Our models will show us what they really mean. Let's begin our demonstration by filling the trailer. Observe what takes place when a trailer is bottom filled. The product from the production plant storage tank is virtually at atmospheric pressure and at its coldest condition. The trailer bottom fill valve is opened and the liquid is pumped through the fill line. Notice that the trailer pressure and liquid levels are both rising. The pressure increase is the result of the inner vessel cooling down. This action causes the liquid to flash or boil as the heat is transferred to the liquid. As the liquid level rises, it acts as a hydraulic piston, trapping and compressing the gas above. If we were to continue filling in this mode, the inner vessel pressure could rise high enough to lift the safety valve, causing an uncontrolled release of the product into the atmosphere. To prevent this occurrence, the trailer vent valve should be left open when bottom filling to allow the gas and heat to escape. Once the trailer is loaded, it is ready to make a routine delivery to a customer site. Certain operating procedures must be strictly followed before the liquid can be transferred into the customer station tank. It's important to operate the right valves in the proper sequence, to cool down the pump and get it running on recycle, and to make sure the pump has good prime. Now the transfer can begin. The top fill valve is opened so that the tank can be filled in the non-vented mode. By opening the pump discharge valve and closing the pump recycle valve on the trailer, the pump discharge flow is directed toward the customer tank. As the level in the trailer begins to fall during transfer, it is extremely important to replace the volume of withdrawn liquid with vapors in order to maintain proper trailer pressure. This is accomplished by using the pressure building coil mounted on the bottom of the trailer. It works by converting some of the liquid to gas. This process is called vaporization. Heat from the air warms the extremely cold liquid in the coils, causing the liquid to boil and convert to a gas. Without this conversion, the pressure in the trailer would drop to an unacceptable level as product is withdrawn. The liquid in the pump suction line would begin to bubble or flash, causing the pump to cavitate or even lose prime altogether. Loss of prime on a cryogenic pump requires immediate shutdown to avoid pump damage. This is extremely important in the case of a liquid oxygen pump because a pump fire could result. By using the pressure building coil and raising the pressure in the trailer just a few pounds, the bubbles in the pump suction line recondense to liquid form and a good prime is restored. Pump discharge pressure has gone up and there is good solid liquid going to the pump, which will provide adequate flow to the customer tank. This process of creating sufficient gas pressure on top of liquid to keep it from flashing is called subcooling. This provides sufficient NPSH, or net positive suction head, which is necessary for good pump prime. Now let's direct our attention to the customer tank. Up to this point, we've been top filling. If we would top fill indefinitely, the pressure in the tank might be reduced due to condensation of vapors to the point where it could no longer provide sufficient product flow to the customer's pipeline. The customer's operations could be seriously disrupted. In the same respect, if we were to bottom fill only, pressure would build up high enough to lift the tank safety valve and release product into the atmosphere. Therefore, in order to maintain proper tank pressure, the top fill and bottom fill valves must both be opened. By adjusting these two valves, the flow can be balanced and constant tank pressures can be maintained. We'll continue to fill in this mode until the full tricoque overflow level is reached. The full tricoque is the maximum level to which a tank should be filled. To go any higher could create abnormal rates of pressure rise in the tank, resulting from insufficient vapor space to accumulate boil-off gases. Let's observe what happens to this liquid if it is allowed to sit for several days with no product being withdrawn. Cryogenic customer station tanks are insulated, just like a thermos bottle, to keep the heat of the air from boiling away the product. But the insulation is not perfect. Some heat does manage to reach the liquid. As the heat enters the tank, the liquid warms and its vapor pressure slowly begins to build. At the same time, there is a decrease in liquid density, or its weight per gallon, and a corresponding increase in liquid volume. Yes, the liquid physically grows. That's why it's extremely important to stop filling the instant liquid comes out of the full tricoque. The amount of cryogenic liquid growth varies. This chart shows the relationship of volume growth versus saturated vapor pressure. Let's review, for example, the growth in a typical liquid oxygen tank filled with fresh, cold liquid near its 0 psig vapor pressure condition. If all the liquid oxygen were to warm up uniformly to a 100 psig vapor pressure condition, there would be a 12.2% volume growth of the liquid. Liquid volume growth of liquid hydrogen for the same vapor pressure condition is even greater. It could have a 22.9% volumetric growth if all the liquid hydrogen were uniformly heated to a 100 psig saturation condition. Remember, in technical terms, the product has reached a saturation or an equilibrium condition when the liquid has warmed to a temperature that corresponds to its vapor pressure. Fortunately, however, uniform saturation does not generally occur in cryogenic tanks. Something called stratification takes place, especially in tall vertical tanks. As the fluid settles, a temperature profile or temperature gradient takes place throughout the whole column of liquid. This tank was filled with fresh, cold liquid several hours ago. The fluid is warmer at the top than it is at the bottom, a definite sign of stratification. It is a known fact that heat rises. In this case, the warmer liquid has expanded and remains at the top because it weighs less per gallon. It is less dense than the heavier, colder liquid at the bottom. Frequently, drivers notice that they get different liquid level gauge readings even though they fill the same tank to the same tricoque level every time. Sometimes the gauge reading is higher and sometimes it's lower. This can be explained by a simple demonstration. Take 3 identical tanks. Fill the first tank with 100% fresh, cold liquid. Fill the second tank with a mixture of 50% cold liquid and 50% warm liquid. And fill the third tank with 100% warm liquid. All 3 tanks are filled to the same full tricoque level. But notice that the liquid level readings are different. The liquid level gauge does not indicate the actual level of liquid in the tank. Instead, it acts like a weight scale. Fresh, cold liquid is more dense and naturally weighs more than the warmer, less dense liquid. The 50-50 mixture of the two falls somewhere in between. That's why it's important to wait until the tank has reached its optimum refill point before making a delivery. That way, the maximum amount of fresh, cold liquid can be delivered every time. Once again, keep in mind the need to fill these tanks to the proper safe level and no further in order to allow for volumetric expansion. Otherwise, the tanks can become liquid full, creating an abnormally high rate of pressure rise in the tank. For example, this trailer is saturated at its maximum working pressure. The liquid volume has grown, and the surface of the liquid is near the top of the trailer. Observe what happens when the vent valve is opened wide. As the pressure of the saturated product begins to drop, the liquid begins to boil and evaporate. It is trying to cool down to a lower temperature that corresponds to the lower vapor pressure condition being created by the venting. Since this is a horizontal tank, the boiling takes place over a rather large surface area and is not too dramatic. Now notice what happens if we duplicate the same venting situation on a vertical tank. The liquid in the upper portion of the tank presses down on the liquid below and subcools it. When the pressure above the saturated liquid at the top of the tank is reduced, the boiling and flashing is much more violent as the liquid tries to cool itself to the now lower vapor pressure condition. That's because the vertical tank has a much smaller cross-sectional area. Notice how only the upper portion of the liquid boils, and as the pressure drops more and more, the line of boiling liquid falls further down the liquid zone. As a final demonstration, let's look at what can happen in the event of a blown rupture disc or a vent valve that has been opened too far. The surface area of the liquid will be lifted up. The boiling process will be quite violent and has the potential to push the foaming liquid into the inlet line that goes to the safety valve. Watch the vent nozzle at the top of the tank. Instead of venting only gas, a two-phase product will be vented, both liquid and gas. This is called entrainment. In time, enough two-phase product will be vented and the height of the liquid in the tank will drop down to a safe level. But in the meantime, a large amount of product is being lost to the atmosphere, creating a potentially serious safety problem. Depending upon the rate of venting, it's obvious that the reactions from depressurization flash loss on a vertical tank can be more serious than on a horizontal tank. So, as a last reminder, take care to fill all tanks to the proper safe levels and no further. This completes our trip through the inner world of cryogenics. But before we leave, let's look back at some of the things we've seen. Condensation, vaporization, cavitation, subcooling, heat leak, liquid growth, saturation or equilibrium, stratification, product flash loss, we hope that you have gained a greater knowledge of the terminology and behavior of cryogenic liquids, and that you'll think about what you've learned when working with them on the job. Keep in mind the need for safe and proper handling when you're loading and transferring these unique liquids, because safety is always our first concern at Air Products.